Hi, my name is Bob Greenyer and I'm a volunteer with the Martin Fleischmann Memorial Project. So here we are looking at E3 section of the inside of the outside from Malcolm Bendel's thunderstorm generator, the 24-inch sphere. And we're going to be looking at these blue spots here. And we're going to be looking at this yellow spot and this yellow spot and see what's going on. And also these black spots that are around here. Definitely some interesting things going on here. So we're going to chuck that into the SEM and see you in a sec. So I think what we'll do is we'll do a quick look at what these things are to settle the debate on those, and then do a map and see if we can find some interesting things after that. So we'll just take a reference shot here. I'll just go to the side of that. Okay. Okay. Put that into the SEM. So it's just taken vacuum from the chamber below here in the reservoir and put it into the observation chamber. So I'm going to do a focus, contrast adjust. And so there we have it. We'll zoom out a bit to see where our structure is now. See, it's not actually so obvious what you're looking at there. I'm going to go straight to the center of this sample. That's our interesting crustacean there, which at the moment it looks like we're on SED. No, we're on BSD, so it's a very even distribution of whatever it is. And we're about as far away as we can get from this. So there's definitely a center line going across there. And we'll do a contrast adjust on that. Okay. I think we'll take a nice high-res shot of this. Okay. I have asked the programmers to remove this rather annoying panel, because what happens when it's doing the high resolution images, it will do the averaging and it will show you the averaging as it's going along. So we can see this is getting clearer and clearer and clearer now. Unfortunately, typically the thing you want to see is in the center of the frame, and this thing covers it up. But I have found out today that they did do one of my other requests, which was to add 16-bit TIFF functionality to the saves, because it actually internally captures at 16-bit. And what that means is that when you go and look at the bright spots here, you can bring the data out of the bright spots. And when you look at the dark spots, you can bring the data out of the dark spots. So it's a much less destructive process on understanding it visually. Now, as I'm looking at this, I can see some sort of crystal structures around the outside. There's a blob over here, which looks very carbonaceous. Most of this looks like rust. But given the fact that it is yellow, I predict there might be a level of sulfate content in there. but we shall see. I think what we'll do is we'll put it into the EDS after we've done a SED image, and then we'll do a couple of spots to get a rough idea. There's a nice bright area down here in the center of this part of the structure where there's a kind of bally-like structure there, but there's a nice bright spot there, and there's a nice bright spot there. So from my point of view, those will be the heaviest elements. So if we're going to find anything other than iron and nickel here, this being steel originally, it's likely to be in here and here. Maybe this little spot down here. I'm going to save this position actually. I think we'll just do a little bit more imaging going around first before going to the EDS. Just saving the image. It's going to be quite large because it's 16-bit TIFF. Okay, so we're going to look at down here and we're going to look at there, I think, first. So I'm going to go center on that. And go in on this. What do we have here? This looks like some rust. What is this agglomeration here? Pull that back down. Quite nice amorphous structure here with this kind of spider web type thing going on. Okay, let's put that into EDS. See what it gives us. Well, there we go. It's iron. And it's probably glowing because it's charging, which means it's got a higher silicon content. It's a little higher silicon here. Pretty clear. We'll have a look over here. Yeah, there's plenty of iron there. There's the sulfur. As I said, this looks like iron parietes to me. Although we got some chromium in there as well. Bit of calcium creeping in. What's this agglomeration here? Okay, probably need to turn up the beam energy just to be sure on this. So let's go back. Put a stop to that. Stop! Right, I need to turn the beam energy up so we're actually... Oh, it's already on 15, that's fine. I've got it on point, so that's okay too. So it's good for SE EDS. Anything else we want to look at? That's going to have more carbon in it. Bit of aluminium in there. So it's steel with aluminium, carbon, oxygen, sulfur, silicon, all the usual suspects. Bit of calcium there, creeping in. Okay, nothing spectacular in that point. We'll go to the other point. Which was up here somewhere. Where was it? Still contrast adjust. Here. So this could be silicon rich or carbon rich. We'll find out. Just I'll do a focus in selected area here. Okay. Okay, and we'll go to live EDS and we'll slap on. Is this iron rich? Yes. It's iron rich. There's a surprise. Oh, or not. Bit of calcium creeping in. But yeah. The components of steel in an internal combustion engine is what we're seeing. Okay. Let's come out of that. Right. There seems to be a center spot here. I think what I'll do is just do an autofocus on that. We'll go to SED to see if there's any interesting geometry. It's definitely built up, and it's definitely got this over this sort of cross section here. Okay, let's see. I want to go to image, and I want to. What do I want to do? I want to change that to SED. Right, so you can see how different the SED is. And actually, I can see that if I go over here, you can see that the built-up area actually extends out a lot further to this more flat space over here. Okay, and this is probably the boundary here. There's a boundary here, this is probably richer in carbon if we put that on. We got the ability to do that? No. We put that on a mix. We probably see this as dark and this is lighter relatively. Let's put that back onto BSD full. Right, so here is the boundary between our ordinary area here and this overall spot. So I think it's going to be useful to do a map of this area because we can't see it all in one frame. These spots are sort of the spots where we were observing either the silicon rich or the iron crenellated microspheres. So let's have a quick look at this one, see if there's anything of interest there. What's that one there? Difficult to tell on this. Go back to the SED. No, that's just detritus. Most of this is detritus. Yeah. It seems actually it's just a general mishmash here on this particular sample. Okay, so you can clearly see there's a difference here in the built-up area. So I think we'll do a map, and then that'll give us an idea of where to look later. And I'm going to do a map on a mixed. What is that? Is that our 2 points here? Let's have a look at that first before we. What is that? Looks silicon rich. Let's see. It's aluminium, potassium, and fluorine. There you go. Wonder if they got any PTFE seals in this device. Anyway. Carbon, oxygen, and a whole bagload of fluorine. Interestingly, 0 iron in this blob. Oh, hold on. It was sneaking in there. Oh, I know what the problem is. Ignore me. I need to put the beam energy. Oh, no, I've got the beam energy up. Put it on point just to be sure. So what you've got down here is the intention here was for image on the previous one, and now I've got it on doing point samples. So now under the live EDS here, I can do a point here, and it'll be focusing on the kind of beam that you need for doing points. Okay, so this has got a squidge of iron in there, creeping in, but it's a strong aluminium signal, strong potassium signal, strong fluorine signal. Okay, we're going to do a map of this area, probably on a mixed sensor. And then we'll maybe even do a map on elements. Find distribution on certain areas that look of interest. Okay. Image. Do I like that more than it was before? Okay. Okay, we'll do that. I think it's pretty flat in this area here. Oh, that's nice. That is nice. We like that. Okay, I think that might be what I go for on this. We'll take one big frame on this, so let's go to sleep whilst this works, and then we'll take a group, a tile map. Do we need to take, yeah, we're going to take one like this. You can see this is the center of the structure, and here's one of the boundary areas here, and that's why we need to do a tile. You can say what you like now, because I'm going to cut this shit out. No one needs to watch that go around for 3 minutes. What do you think?
I don't think anything yet.
Do you think it's iron and sulfur, like I said?
Well, this wasn't the gold. The gold was a little dot next to it.
Oh, where? What?
Yeah. This is what Malcolm was saying. There's
Okay.
a little micro dot next to this.
A micro dot, like this one?
No.
Tell me where.
I'll show you. Screwdriver.
Okay.
You know, this was pretty clearly sulfur.
Mm-hmm.
Oh, you know what? I have that macro lens that is the.
So do I.
I took photos of all these.
Mm.
Would it be helpful to bring that up on my laptop
Yeah.
if you wanted to
Yeah.
look at certain areas without using that same?
Mm-hmm. Okay. I'll do a save position on that. And I'll go to the map here. And I'll So where's this thing you're talking about? Is it this one or the other one down here?
No, it's the little guy right next to it. No, like on the bigger screen there. Yeah, it's that. Hold on, there's. Yeah, so zoom out a little bit. Go to the other one. Can't tell. Okay, so no. So it's near. Zoom into that bigger one.
This one?
Yeah. Just a bit. Okay, we go to the left. Okay, so I think it's that little guy right there.
Okay.
I think.
It's got a nice feature in the center. Looks like more rust to me.
Yeah.
I mean, when you see these kind of structures, that's iron oxide. Anyway, it's quite a nice structure.
I think it's that. Let me bring up the photo. Yeah, so the spot in question, Bob was right here.
Yeah, okay, coming.
So I think you are on it.
Yeah. Yeah, that's the guy.
That's it.
Yeah. Okay, well, we'll see what it is. I can rotate it. There we go. Get a nice overview. Yeah.
Yeah, that's definitely the same one.
Mm-hmm.
Here, it's pulling up a little bit.
So I will do a map on this. Yeah. What are we on? Looks like one of our little friends up there. That's the same thing.
Yep.
Yeah.
No, I know. So you can see.
Yeah. No, I haven't, but it's good. That's actually the other way up.
Yeah. You flip it?
Yeah, just rotate it 180 degrees. Yeah, that's closer. Okay. All right. New. And this is E3, is it?
Yes.
Do a couple of points. So let me see that. Okay, so you've got a definite feature there. So we'll have one of there. Iron, chlorine, silicon, sulfur, mostly iron oxide. And we'll have that one. Oh, that's nice. They've also updated that. They've got 1, 2. They've got these number spots here, so they actually got a 1 next to it. So you can actually see. Right. Normally, in the past, it would just highlight the spot.
Yeah.
But here it's showing the number next to it. So. Okay. So yes, you've got more sulfur on this one. And then the other one, you've got like a splodge up there. Another spot on that. So that first one is mostly rust. Of course, EDS cannot see hydrogen. So if it's rust, you can't see the formula of rust because you can't see hydrogen. Yeah, so that's got 2% sulfur in that one. Got a chunk of nickel in this one. It's fairly high in the nickel. Chrome. All sort of steel components. Let me do a map on that central splodge here. Well, that's interesting. We got a whole chunk of calcium in that central spot there. That spot there. Yeah.
Calcium.
Yeah. And a lot of sulfur. There we go.
Yeah.
Yeah. So that might be the twinkly bit. What is the formula of iron pyrites? It is FeS2. That could be FeS2, although look at the iron. There's almost no iron at all. That's calcium sulfate, actually.
What about this little bit right here?
That bit there?
That'd be like that little spider egg guy.
Yeah.
More the same.
No, that's iron and oxygen.
Yeah.
So calcium sulfate, rust. I don't think that's praseodymium. That looks better, chromium. Right, we'll do a basic map of this area and then set this one to bed. Yeah, so it's got a lot more oxygen there. Carbon's around the outside. Chromium's around the outside, nickel's around the outside, so you're seeing the steel more on the outside. The sulfur spots are definitely in this. Look here. There's a defined sulfur areas. Silicon is everywhere. Calcium's co-located with the sulfur. There you go.
Huh. If the sulfur were being extracted from the fuel, do you imagine it'd be concentrated like that?
You can definitely get concentration, can't you? Like, so maybe. It's why you get calcium and sulfur co-located. You have to have an explanation for that. So it might be interesting to have a closer look at one of these spots. Yeah, there's nothing interesting there. It's the calcium sulfate, and that's the story of these things. It seems to create calcium sulfate, and that was a lot on the top in that sort of what Malcolm likes to call Stonehenge. So I think we'll pick one of these spots, either this one or this one, to have a closer look at. It's still doing the samples here, but if I go here, you can see.
That middle one looks like the most concentrated.
Yeah, that's actually what we clicked on earlier. So if we go
yeah.
back to this one,
Oh, yep.
look at the sulfur content on that.
Yep.
I mean, this is calcium sulfate. But then you've got to ask, why is that in the center of this structure? Why?
Well, and why is it nowhere else?
Why? Yeah. So there's that.
Sample.
Like, so, well, it is in the Stonehenge, but like you go here. No, well, hold on. Let's go to the calcium sulfate. The sulfur isn't on the outside of this structure. It's all in this structure. Okay. When you have a dull look like here of something, that means there's nothing there because it's everywhere. So it's not really a sensible detection. Where's the sulfur gone now? Why has the sulfur disappeared? Come on. It's there. We know it's there. Aluminium. The bulk of it's still iron and oxygen, but right, so it's finished that map at the specified sample settings. Aluminium's on the outside of the structure, on the periphery. Look. The chlorine is on this side of that central feature. Yeah, you see? So that might be worth doing a spot here as to why that is there. It's going to let you do that.
That's just right next to where you already sampled, though, right?
Hold on, why does it not let me do that?
Yeah, you got.
What do you want to call this?
Fool's gold.
Okay. On the map. See, the oxygen is rich on the ridges. That might be where it's just catching the beam, though. Carbon, chromium, not really that interesting. But yeah, the sulfur here, particularly in this spot here. And then calcium co-located. And where did that chlorine go? Where's the chlorine? That's not showing it, is it? Oh, there we go. Yeah, that chlorine is just in that spot there. Interesting. This might be the center of the action. And typically you find the calcium is in the center of the action. Yeah, so that is the center of whatever this was there.
Yeah.
You get the calcium in the center. And these are kind of like self-similar type structures around here. So we'll have a look at that separately, but we'll go and zoom into this particular structure here a little closer, which is here, right?
Yeah.
And the other one is here. So this is self-similar. We'll have a look at that first, actually. I mean, it's definitely got form, hasn't it?
Doesn't look like a whole lot going on.
No, but it's centered around this thing here, and it's definitely different from this.
Yes.
Okay.
And on the macro shot, that's this little area right here. This little ring strip. Yeah.
Hello.
Hello. Do you remember that?
Yeah, see by atoms.
Yeah, it's just rust.
Well, it's iron and oxygen, but by atoms, you've got almost as much calcium and sulfur as you have iron. And that's over this whole area.
Where do you think the calcium?
So the iron's on the outside, look, that's a defined area around the outside.
That's kind of the opposite of what you usually expect. Right?
And there's the calcium inside that. Look, that's highly marked.
Where do you think the calcium's coming from? The water?
I would argue that the calcium could be transmutation.
Well, obviously that's on the table. I'm saying absent that. What other source?
Obviously the water.
Yeah.
You're not going to get it in the methane, are you? There shouldn't be a lot of calcium in the methane. So yeah, it would be the water, but it's the fact that it is inside this structure, which is clearly the central spot. And that is highly demarked. I mean, that is, it's night and day between those two things. Yeah. Look at that. It's just totally conclusive in terms of it not being here and it is there. And that's the same with the calcium. Calcium's the same. They're about as co-located as you could get to the co-located things. Like exactly and only. And here, not at all. What else we got? The nitrogen's everywhere. The chromium's everywhere, so nowhere.
No, are you seeing that in
carbon.
Bin's system at all? The calcium and sulfur
Oh,
co-location anywhere?
well, calcium is always at the center of these spots. If it's not iron, it's calcium. But since you're starting with iron, that wouldn't be that interesting, right?
Right.
But like in the spot where the clear center of the vortex came down on a wire in a Lion reactor, it's got calcium is the new element because it had aluminium oxide and silicon oxide in the reactor construction materials, and then it had copper, which is inside the silicon oxide, and it had iron, chromium, and aluminium. So the calcium is crystals, and the calcium was in a vortical structure on the top only of the wire. So you had a 12 millimeter sacred geometry magnetohydrodynamic structure with a center spot here, and the center spot here was on the bend of the heater wire. And the vortical deposit of calcium structures was only on the top and not on the bottom. So the flux was coming from one side down, and the only source was silicon dioxide and aluminium oxide, but then there's calcium on the center.
Yeah.
So this is consistent, and of course sulfur, if you're getting fusion to calcium, well, sulfur is a fusion of two oxygens. So if you're going to get fusion, we've absolutely shown that in the HHO, which you're going to have in the system on a 10 yen coin, there was a copper oxide only, and then there were these little balls that had taken the oxide off the top and made sulfur. So categorically, sulfur and calcium are signs of transmutation.
Are there signs that...
and they're in the right location. You could call it concentration, but there was no sulfur in the 10 yen coin, and there was no sulfur in the air, and there was no sulfur in the gas we were putting on. Yet there were sulfur balls, where the oxygen had been taken off the copper. Right. So sulfur is a synthetic product of ball lining. Yeah. Absolutely, we've proven that.
It's been said that there's no sulfur additive in this fuel source. Obviously, we don't know if that's true or not.
We don't know, but the point is that sulfur can be synthesized by ball lining, right? And by the magnetohydrodynamic structure, you've also got the production of calcium conclusively in the Lion reactor. And here you have two typical things to be formed in the center of one of these structures at some level of fractality. And they are specifically not where the iron is, which is the starting material. Specifically not where the iron is. Very, very exactly and perfectly consistent. Now, we'll do another map on the other one to see if the fractal structure is similar, the one on the outside. Because if you look at the work of S.V. Adamenko, he saw a kind of like a black hole object. He was firing primary ions to it, and the material was consuming the primary ions. There was the around the outside, he also saw regular spots which did the same thing, fired the primary ions. So it was the same thing, but it's much more intense, this system. So let's see if we see the same kind of structure on the other one on the outside. So the other one was over here. So we've just been looking at this one, haven't we? Where are we? Sulfur and not chlorine.
No, we're looking right over to the right.
Yeah. No, we're looking at this one. Exactly. So that's where. So we want to look at one of these other ones, which is on the periphery.
Yep.
So we'll go.
Go that one.
Go there. I'm going to punch that in, and we will come out. So it's here. Yep. And you can see this is a much more intense area than this is. But will we see something similar in terms of the story? Let's check that's actually in focus.
So, Bob, did you try the EDS?
Oh, I haven't. It's working, which is good news.
Yeah.
For everyone.
Yeah, it was just one cable.
You know, I went to America, and my wonderful director and colleague and friend, he couldn't get the Cirrus 2 gas mass spectrometer working, and he thought it was a major problem. Phoned him up, blah 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 blah. It turns out that the UPS battery that he was powering it with was not sufficient to take the surge current when it was turned on, so it did an error and wouldn't work. And that was it. Yeah. As I always used to say when I did computer repairs, have you turned it on?
Yeah. No,
Have you plugged it in? Those are the first two questions.
Yeah, from the British sitcom, do you try to turn it off and turn it on?
Yeah. Right, okay, this is interesting. I think we're going to see maybe a similar pattern here, but there's no guarantees in life. Okay, so we'll take another map here. Well, look at that. I'm already seeing the iron on the outside, the sulfur in the middle, and then the calcium. It's the same story. So this is showing a fractal structure. And this is very much like was observed by S.V. Adamenko, and it was reported on the APEC Tim Ventura's interview with S.V. Adamenko.
So do you think it's...
Look, that is like exactly the same story.
Yep.
Totally conclusive.
Yep.
The same story.
Yep. Now, do you think it's drawing material from its immediate environment all around it, or do you think there's a point, a yang point from which it's taking through that vortical structure somewhere else here?
I think you've got the main structure in the middle, and it's attracting other structures that are self-similar.
Oh, so there's little satellite vortices that are spiraling off?
Yes. And you could argue it's vortical concentration, but we already, as I said, HHO, which is going to be in this system whether you like it or not, because you're injecting water, right?
Yeah.
Right? HHO on 10-yen coin, there is no sulfur in that entire system, and we see sulfur synthesized in little balls which have extracted oxygen.
Yep.
Everything you need to know, it's on snowballs on cobblestones on the MFMP YouTube site, that video. And then separately, on analysis of line, you're getting calcium in the center point on the top side of the flux loop. So you know the flux came from here and it crashed down on the top of the wire. There's nothing on the underside of the wire, and it's got calcium where there's no calcium in the material. So at the center of both types of structure, you're getting, in one case, sulfur and one case in calcium, right? And so I would say this is conclusive, in my view, of this process being undertaken. Because you wouldn't expect a lot of calcium in there, although you've got water. You certainly wouldn't expect a lot of sulfur, although you've got natural gas, which might have sulfur in it.
And if you were extracting sulfur from the fuel and calcium from the water, what are the chances they would always end up in the exact same place?
Yeah.
Seems unlikely.
Yeah. I mean, at the very least, you've got a novel concentration method. Right. You've got a natural vortex separation system. But then why does a vortex concentrate specific elements at the center of its structure? Not on the outside. Typically, you get heavier elements thrown to the outside and nothing in the middle. You know, when you centrifuge something, all the heavy stuff goes to the outside, right?
What's the...
But these are specific elements, and like sulfur's much lighter than calcium, right?
Well, usually you're getting the ferromagnetic structures in the middle and the paramagnetic structures thrown out, right? But this is the opposite.
Well, I wouldn't necessarily know whether that was true. Look at that. I mean, that is...
Yeah.
there's your iron and oxygen, right? They are... So that's oxygen. That's iron, right? But this structure here clearly is telling that story. And look at it. It's a freaking hexagon.
Yeah, I didn't even see that.
It's literally a hexagon.
I didn't even see that. and just even the grain orientation.
Well, it's pointing into the main structure.
Right. Yeah, exactly.
There's a kind of a pulling in.
Yep.
to the main structure.
So I wonder if we look at another dot.
I mean, look at that. That's just hilarious. It's so demarked.
It'd be interesting to check another dot and see if the grain is similarly vectored towards the
pointing.
middle.
Yeah. Okay. So let's do that, shall we? So we're going to call this peripheral 1 or orbit 1. No, peripheral 1. There's no sign it's orbiting. It's still doing the map, so I'll leave it to finish the map properly. That is a hexagonal structure, and it's really rather beautiful. Even look, the chlorine's on the outside, the nitrogen's on the outside, the nickel's on the outside. What was that? The chromium's on the outside. Yeah. All of the things that are in the steel are on the outside. Right. And there's this new thing in the middle, which we've already, in my view, proven conclusively could only come from this electrodynamic system. Because it's literally in a ball on snowballs on cobblestones, and it's from HHO. And it's where there's no understanding that there's HHO, it's on the top of that wire, when there's no calcium involved in the system, right? And so it came from, in one case, we showed it's in a ball from an HHO system. In the other case, we showed it was in the electrodynamic core.
So, I mean, just thinking out loud, if it was a case of simply a sort of fuel-water combination, like a droplet settled on that spot, and that's accounting for your calcium and sulfur, and it's sitting on top of
a droplet.
The metals.
Why isn't the droplet round? Why is it hexagonal? That is hexagonal. There's no way you can paint that as not being hexagonal.
And it looks like
and the co-location is so perfect. Like even these little licks and stuff. They're you know, that curve there, this bit here, they're exactly co-located.
Yeah.
I mean that look at that. It's just freaking totally bang on. Right, and what is the scale on that? Let's have a look at the scale on that. We're on 3 micron there.
So about 15 microns across. A little less. 12.
Yeah, if I pull out, let's see, it's
about that.
It's about 15.
Yeah.
No, I'd say that's 20. This is our sort of normal kind of structure size.
20 to 30 is the shoulders sweet spot. Right?
Yeah. 20.
Yeah.
Yeah, it's just establishing the orientation. But that definitely has a flow pattern that way and a flow pattern that way. Okay, so let's go and have a look at one of these other ones.
There's another one that's pointed.
Yeah. So we'll go back to this one and we'll look at the map and we'll see.
How about that one?
That one there?
Well,
that's on the opposite side.
But we want this one to see if it's pointed down.
Oh, that one as well. Oh, do you want? But this one's clearer, isn't it?
Well, I only wonder
because
maybe there's a process by which they'll, kind of accrue or accrete horizontally. But if it's at the top, and it's pointed down.
I buy your argument. I buy your argument. Okay. So it's looking at. Fortunately, we can see it quite nicely on here. So this is another feature. It's not as this is the next best thing, if you know what I mean. Let's say
it does. It does actually.
It's actually got like that kind of thing going on.
Well, and look at the boundary does look vaguely hexagonal again.
Well, let's see when we do.
But it doesn't look like the grain is doing anything very interesting.
Because we got to understand where all of that calcium sulfate comes from at the top of the dome in the so-called Stonehenge, right?
Yeah.
And this would help to explain if it's being made in these structures, and then it's aggregating at the top, which is like a superstructure of the overall substructures, if you know what I mean. The whole thing is effectively acting as an accumulator.
Right.
But this is helpful because you could see that the top of that thing might be a vortex separation. But in this instance, you're seeing the iron is all the way round, and you're seeing these hexagonal structures. I don't know whether this is going to be hexagonal, but the other one was clearly hexagonal.
It kind of, just based on the the boundaries of the light and dark. I mean, the left side looks a little infringed upon by whatever this lumpy thing is here, but the other side looks like it has pretty distinct size.
It's not as clear cut,
No,
but
same deal though.
the sulfur there,
Yep.
it's very much the same story.
Yep.
And it does seem to have a central feature here.
Yep.
So it might be that your non-radiating boundary is here of the bulk structure. And
Right.
my argument
And that's
is...
your little counter vortex.
Well, my argument
rotating.
is that these things stick onto the outside
Right.
of that non-radiating boundary.
Right.
They're attracted, but they can't punch through.
Right.
Unless maybe they get so...
Or they're emanating from it.
It could be. But like, if you look at the... if you look at the structure that was produced by the Shakhparov generator, the white one, it had the white sphere and then it had little lobes on it.
Mm-hmm.
I mean, look at that. I mean, it's exactly the same
Yep.
story.
Yeah.
And you could argue that that is distorted hexagon in a way. You know, you've got a point there,
Yeah.
point there, point there, point there, point there, point there. So you've got to think there's a pattern driving this, but there's all the other forces in the system.
Right. Exactly. Yeah.
Whereas the other one you might argue that it's kind of like, I mean, look, it's the same story. It's the same story.
Yeah, for sure.
I would say that is. It's a hexagon.
It
but
wants
it's
to be
highly
it
distorted.
wants to be a hexagon.
Yes. Yeah. And this is where you just do more data.
You want to hit maybe one more of these?
Maybe hit one more, but I think we're seeing.
I think
patterns.
it's going to be
Really,
one,
and it's a beautiful thing in its own right, and it's important data to understand the overall process that's going on. The fact that you have this overall structure that has a central core, certainly, and then these peripheral objects that are around it, which are only in this overall structure. They're not in the greater area.
Now, was this happening in the very middle as well? Was this what we also observed there, that central point, where there was also a sulfur?
The center here, it's a distorted hexagon. It's 1, 2, 3, 4, 5, 6.
This is the center of the
This is
entire
the center.
macro object,
Yes.
right? Yeah. Okay.
So you've got a distorted.
Right. Okay.
Now I wonder if these point out to those substructures.
Yeah. Right.
I don't know whether they do. Does it? You got one
Well,
there, one there,
six.
one there.
1, 2.
Let me get the map on here.
There's kind of
I don't know. No. I'm not buying that argument.
no.
So we looked at that one, did we?
Yeah,
Look at this one.
Yeah, let's try that one.
Yeah, okay. It's still doing the map over here. But I mean, it's just like... If I put the sulfur on in both. Right.
Yeah.
I see a pattern here.
What's the size of this one? Is this also 20 microns?
Well...
Or is it a little larger?
We can go to the image library whilst it's doing this, and we can have a look at it. Yeah, so that's 20 microns.
Yeah, about the same.
Yes, it's about the
Yep.
same. Yeah. I mean, that is very clearly a thing.
And the distance from the center point to the rest of them is somewhat different, but it has some. I mean, it's sort of squished, a bit oblong, but it's relatively consistent. I wonder if this one down here almost has a little more concentration. I guess that's probably a bit of a better shape. Yeah, let's go with that one. Yeah. Oh, that's the whole.
And here's the thing: it is actually happening out here. The same story.
Mm-hmm.
They're slightly located, but then they've got big ones here, and then the biggest agglomeration in the center here.
The moons of the planets. The mini one.
Well, I see these like stellar constellations.
Yeah.
It's the same forces driving all of these things at different scales.
I agree.
So we're going to have a look at that one. Okay, so I'll come out, and it's this one here, right? Yeah, we got a friend over there.
There he
This
is.
interesting.
We'll look at that center ball.
Yeah. Definitely, this is definitely a story.
And look at the hexagon.
I'm not calling it right now, but I think you're not wrong.
You can see it.
Yeah.
It's a little boxy up in that top right, but
Yeah.
it's almost more like a pentagon.
It will be one of the two.
Yeah.
You've even got a similar thing going on over here, so I think we'll map over that whole area.
I know Malcolm's gonna kill me if I don't ask about this angle right here.
Yeah.
It looks.
I'll let him work that out.
It's creeping up to 51 degrees. It looks like.
Okay, so let's get the contrast on that. I kind of prefer the previous contrast anyway.
Yeah, it's gonna be the same story for sure.
Dobija, telefonowałem z takiego.
Okay, so I'm going to call this Peripheral 2. I'll get that going first. Take a map over that area. Well,
Yeah, there we go.
it's got some detritus that's fallen on
Yeah,
it.
yeah.
It's breaking our perfect hexagon.
Well, you can still kind of, there's definitely still a little bit of definition. No, look, there it is.
Yeah.
For sure.
Yeah. Oh, very nice one.
Well, thanks.
Well,
I'll take it.
that was very good, yeah. That's a finding right there.
Yeah.
That's highly consistent.
Wow. And it's interesting that the distorted part at the top is closer to that center node.
You have a distortion here that's pointing towards the other structure. This one that's in the center has distortions pointing out.
Right.
This one's a little bit all over the place. But I think the major distortion is pointing down, isn't it? So that's the one at the top. So, like, that's...
That's that corner diagonal one.
That one, yeah. But it could be like this one's being affected by over here, but this one's being affected by this one because it's a relatively strong one.
Real quick. So can we take a look over here? Because in this one, the center node is at the top.
This one, yeah.
Yeah, I'm just wondering if it's offset in the same like clockwise pattern all around.
Yeah, I mean we can actually go and have a look at some of the other ones, right? So
it didn't appear. You just clicked on the left structure.
We can look at this one,
Maybe
and we'll let's go around the thing. We'll look at this one as well.
Bring around the rosy.
Yeah. But I mean, look, you couldn't get a clearer signal. This is definitely a thing. Just for those that are looking at this right now, this is essentially iron on the outside and sulfur in the middle. And we can switch over to calcium. And in every single case of these structures, the calcium and sulfur are co-located in these distorted hexagonal type structures. As I say, you can't always get what you want. But if you look, you might find something.
But if you try for 4 months. you might get dots of co-located sulfur and calcium.
Exactly.
That was the first version of the song.
That was
catchy.
yeah. Yeah. They realized maybe they needed to work on the lyrics. Yeah, I mean, this is definitely a story. Yeah. It's interesting. This one's like very much a piece of calcium at this point.
So if that center is settled at the top, and if all of these substructures are spinning around the center structure,
I don't think they're spinning. I think they're individually spinning but locked in location. If they were spinning, then there would be a smear around the outside.
Yeah, sure.
So these have found a resonant point,
Right. So
and,
these are
and
standing
in their
wave nodes
relationship
where-
between each other,
Yeah.
and they're stuck there doing their job.
Right.
Okay, we're done on that one. So which one are we going to go for next? This one over
one of the
here?
lower ones, yeah,
One
yeah.
of the bottom?
Let's try
Or
that.
we'll try that one.
Whatever one's most concentrated.
Well, we'll do that one there because it's on the opposite side to the ones we've been doing up
Sure.
here. Okay. So getting a little harder to spot here.
It's the skull-looking guy right there.
I think it's this thing.
Yeah, it's the skull.
Uh,
It'd be interesting to check out these
that one,
concentrations. This like
below
very high
those
concentration of iron right here might be interesting at some point.
yeah. There.
Yeah.
Under those two. Is it here?
Yeah,
Is
it's
it
that,
this?
that's it. It's that skull. Yeah. Is it a hexagon? No.
I don't know because it's highly built up, isn't it?
Yeah, this one's a little
Uh,
lumpy.
we'll know if we hit it right because it'll show the pattern or not. Hey, what happened there? What happened? Why is that not doing it? Okay. All right. We missed it. It's there.
Huh?
It's there. We missed it.
You sure?
Yeah, I'm pretty sure. Look. Oh, no, we didn't.
No, that's it.
Wow, that's a triangle.
Star David. 2 triangles.
Oh, it's right on the pinnacle there.
Look at the inverted triangle poking through.
Yeah. There you go.
Which is a hexagon.
It is a hexagon. Yeah. It's just very subtle. And I think that's the one we were actually targeting there.
It's a hexagon. It's just got like 2 stubby legs.
I'm going to kill this and I'm just going to move over and get those two together because
Sure.
we get that was the one we were targeting. We're
Okay.
just a little off. So I'm going to stop that. And
So I know we've talked about this
yeah.
in the past, and I have my thoughts on this, but why do you think the hexagon is generally the default shape for these structures?
if you have 6 arranged in a loop, it's really stable. Because
Is this because it's the
When-
poles
when-
of 3 THORs, 3 sub-THORs?
well, it gives you the flower of life.
Yeah.
And when the disruption beam actually goes all the way into the main vortex core, and so it holds itself together very strongly.
But
And it takes stuff in, and the stuff gets stuck inside.
so is the result of 3 sub-THORs that produces it? Because you're getting the poles?
If you get 3, you don't get the disruption beam going into the apple, or you don't even get it going into the sphere. So, like, you got the non-radiating.
Because it's got to be even, right?
You got your. Let me get it started, and I'll explain it.
Sure.
Here. Did I get them both? Yes. If you must have 2 minimally at a fractal level.
Right.
There you have the disruption beams coming out. That gives you your spiral galaxy with 2 arms. Okay, that gives you your normal yin yang.
Mm-hmm.
If you have 3, you get your 3-arm, 3-legged or 3-spiral arm galaxy.
Mm-hmm.
If you get 4, the disruption beam just catches the edge of the non-radiating boundary.
And when you're saying disruption beam, are you talking about the longitudinal hyperboloid vortex that is funneled through
its main distance of
the
influence.
mouth, right?
It's what pulls the material into the arse. Yes.
Right, that point of the sacred geometry where it's pulling.
Yeah, imagine it
material
like
down.
a sea urchin.
Right.
It's the mouth on a sea urchin.
It's the mouth on our face.
It's mouth on the sea urchin.
Okay.
The sea urchin's the right shape. It's like that, and it has a freaking
But so
mouth.
is this, right? It's like, here's the
Oh
disruption
yeah,
beam,
yeah.
and
It
this
is
where we
but
destroy matter.
We're a
right?
2D section through a sea urchin.
Right.
A sea urchin's almost perfect in terms
Right.
of the shape,
Yeah.
and then it has the mouth right in the center at the bottom.
Yep.
Okay, and so that's the bit that's eating in. It's like a freaking apple. How do you feed an apple? You feed it through a stalk,
Yep.
right? And it grows out away from the tree.
Right.
That's literally the same model.
Yep.
Okay, and so that stalk of the apple on a swastik starts to go into the apple of the one in the ring, around from itself. So that is less likely to produce a disruption beam coming out. And then you start getting a more focused beam coming out of the N-level THOR.
Mm-hmm.
Okay? Because it has less vorticity, and it's just more like a directional beam. Okay?
Could that also be the result of that in like a tertiary structure, there's no way to evenly divide it, whereas with 4, you have a definitive pole?
No. The rotational,
It's coming
the
up
mouth
through.
beam, the
Right.
tractor beam. It's
Yeah.
like, imagine it. I called it a tractor beam a long time ago.
Yeah, so it's
The tractor beam
perpendicular.
is half inside or at least nearly inside the non-radiating boundary.
Mm-hmm.
It kind of still these things can punch through their own non-radiating boundary, so they can kind of what they don't seem to be able to do is to punch through the apple. Right? So if you have 5, it starts to the beam starts to interact with the apple, but not entirely. It's only when you get to 6.
I mean, when you say interact with the apple, do you mean that it's reintegrated into
The
that
matter
vortex?
comes in through here,
Yeah.
and it's the only way it can come in
Yeah.
when you get to 6.
Yeah.
When you get to 6, the disruption beam, the mouth from the one next round the loop is actually inside the apple of the one behind
Right. So
it.
it's just feeding itself.
Yeah,
in
so the only beam that comes out is the main beam that comes
Right.
out. So
Right.
this is why you typically see 5 or 6.
Right. The N+1 beam, right? The macro
No,
THOR.
the N beam.
Right, yeah.
The N beam is the only
mother,
beam.
Mother beam.
The mother beam is the only beam in town when you get to 6.
Right.
When you get to 5, it's pretty much the only beam in town as well.
Okay.
But when you get to 4,
so they're kind of, because there's less structures to capture their output, they're more likely to shoot off and produce little bits of coherent matter out to the periphery. Is that what you're saying?
That's what happens when they break down.
Okay.
They spit out through their weak point.
Right.
Right now, if you've only got a 2-order structure, like we're seeing in a lot with bin when
Then it's just spitting.
No,
everywhere.
each of the structures, if their subtor is maximally, I mean, they can have many more inside the n minus 1.
Right.
The n minus 2, there could be a lot of n minus 2s, but the n minus 1, if there's only 2 of them, they will have a beam that punches through, and that's what you're seeing all over that DZI image which I shared.
Yeah.
All over it.
Yeah.
You're seeing these structures,
All
and
those
they've got a hole on one side.
The mini Oreos that are...
No, the mini Oreos are the n minus 1 or the n minus 2.
Yeah.
No, n minus 1. Like they're the tore down.
Okay.
And the mini, well, it depends. Like the Oreos or mini Oreos.
Right.
You're making a new terminology here.
Not the micro Oreos. Just the mini Oreos.
Oh, well, look at that. That's a very, very clear story again, isn't it? So I think we've established something here. I think we don't need. I think we don't need this one, do we? There we get rid of that. I don't think we need that. Okay, so bomb, and the center one. I think that's done. That's told the story of the key component on here, which you can see from this. The rest of it is the stuff you expect in the material.
And I almost wonder if, not to be...
Oh, you want to have a look at this?
Well, I do want to look at that concentration of iron, but I wonder if these little bits, right, if we get these micro vortices, I mean, I think we know what it's going to be.
Well, this is going to be mostly iron, isn't it? So.
Well, no, I meant still the sulfur calcium. But, because these are these kind of sub-satellites, but I think we know what it's going to be.
Let's find out.
If we go to one of the very small ones in the extreme periphery of the structure.
It's this structure here, I think. There, is it?
You could probably kill 2 birds with 1 stone if you get this whole bit there. Take a look at that iron, and then maybe one of the sulfur calcium.
To see, because these look like a regular version of this.
Right, exactly.
So I think this is processes occurring everywhere.
Yeah.
And so
let's check out that one. Check out that iron.
I'm just trying. This is a Q point here. So we got our 2 blobs here. Okay, so we got 2 things up there. Here, it's that thing there. I think this little structure here.
This might help to
That
navigate.
one or that one? I'm going to do a medium shot here with just a quick map. Let's see what happens if I do this. So we were over here. Is it that one? Am I looking too far away? It's just down a bit and to the left. Now look to the left. Somewhere here, isn't it?
It's going to be hard to see him not this far.
I'm pretty sure it might be this. Anyway, we'll do a map here and just get a quick idea.
Oh, let me.
Oh dear.
Well, we know. Okay, so.
That's
it.
I know. That's good.
Because you kind of got these three
Yeah.
pointing to it.
Carbon. No, get rid of that. Remove measurements. Right. Okay. Right. So. That. Oh, there's that little bit there with that very identifiable structure there. Okay, there's the. Okay, so it's to the directly to the right of that. So it's here, I think. There, yeah, there's the two structures. This one and that one.
So that's your iron bit right there?
I think this is our iron bit here. Yeah. So we will take a thing here, and we'll do a map there. This looks like calcium down here. Right.
Oh, sorry. I thought you were taking
sorry.
a picture of me.
No.
What were you showing me?
Have you answered?
No. Well, a little bit.
Right, there we go. Yeah, we definitely found our iron culprit here. Ah, interestingly, this is aluminium. That one. And the aluminium's co-located.
What percentage? 0.9?
Oh, we'll look in a minute. This is the overall area, so we'll look at the two points individually now that they're identified. Oh, potassium and aluminium co-located.
Huh.
Iron, potassium, and aluminium co-located. Well, that's interesting. I'd like to know where it came from. It looks like an eruption of some type. Right, so we will have a look at those two things, and then there appears to be two silicon-rich blobs in between. Now you see how it takes so much time.
That's what it takes.
We're looking at a couple of blobs.
I know. We're an hour and a half in. Well, we have 70 samples to go. So
We've got 3 samples to go at most. That's right. I'm going to use a Malcolm phrase. Ruthless prioritization.
did you want... So we have... we can talk about what we get into after this. Is that still mapping out?
Yeah, but I'm going to just set up some spots for it to do afterwards.
Because a lot of these are pretty similar. There's a couple like mega sulfur samples. I don't know if you want to look at those, or there's that interesting
I think we'll look at one. Pull out one of the sulfur samples because I might put them on.
And then
the
there's
map.
that spiral structure that I sent you a picture of. I don't know if you want to check that out.
Mm-hmm. We've got to look at some of the blue areas on this.
Yeah, definitely. Four. No spheres yet. No spheres yet.
Well, not looking for them, are we?
No, really.
I think you'll find that they're mostly up in the pole because
Yeah.
they're magnetic,
Yeah.
which is where the sulfur structure is. What's going on?
So Malcolm was worried about making sure that we had enough sulfur samples for the isotope work. I
Yes.
think we have a ton.
Okay, good.
Now, does putting them in
What? That's not something I expected.
what?
This structure here, the one that's hiding aluminium,
Mr. Shrimpy
is
guy?
42% fluorine.
Fluorine.
Yes.
Huh?
Yeah, huh? And that's the next one on from oxygen. That's adding a hydrogen to a proton to oxygen.
Yeah, that's just, well, it's 9, right? Fluorine.
Well, it's 19.
19.
So you take 18 oxygen and add a proton and you get fluorine.
Huh.
I mean,
Interesting. Why?
I mean, it's 24% fluorine. Add helium, and you get potassium. Roughly, is that right? 19. No, that's not. I'm talking rubbish there. That's interesting. Very. I mean, look at the nickel. It's like, where's the iron? The iron's by weight, but by atoms, iron is just 8.4%. This is mostly fluorine by atoms. That is interesting. I don't know what it means.
I mean,
But I mean, that is this very, very strong peak.
I mean, if you're adding protons,
We'll do another
somehow,
sample on there.
because you have one down from, what is it?
It's exactly the same story. Look at that. 46. 45% fluorine. That's 30. I mean, this is even stronger.
Yeah, because you get, if you're stacking protons, if you put one into argon, you get
Now, fluorine comes
potassium.
You take oxygen 18 and you add a proton and you get fluorine. Fluorine 19. No, we're looking over here.
Oh, yeah,
Over
yeah,
here,
yeah.
Over here, over here.
Oh yeah, I'm looking at just protons.
It's 19, so
Yeah.
you have to have oxygen 18. So this encourages me that we might see some sensible amounts of
Right,
oxygen.
but what
18.
wasn't the other one potassium you have in there?
Potassium, yeah.
Right, but yeah, you get that from adding one of the argon, which is in the system as well.
Yeah. A reasonable amount of argon to start with, yeah. Okay, so, and this is our iron-rich lump. What? That's also a shed load of fluorine. What's going on here? Now I want to go back to my map and ask it to look for fluorine. Can we add fluorine in here? See what it thinks. Yep, there's the fluorine. What is that about? Because the fluorine is co-located, in that case, with the potassium and the aluminium. Like, what?
So where might an exterior source of fluorine come from?
Well, PTFE. If, like I say, if you had a Teflon seal somewhere in the system,
Okay.
right? Or
Yep.
maybe you had some, I don't know, some sort of Teflon-based sealant or lubricant. I don't know. But the interesting thing is it has aluminium in there.
Which is co-located
And
with fluorine.
but yeah,
it's right on top of
exactly
it.
like potassium.
Wow.
Potassium fluoride with aluminium. I mean, it's like, what? Doesn't make a lot of sense, does it? So, not entirely sure what to make of that. That's, that is a little odd. And these structures here with the silicon here are in the middle, aren't they? So go back here. That one there. That's definitely silicon. That is basically okay, so that could that come from your cutting disc? I don't know. Have you got any of your samples of your cutting discs? That would be good to have a look at.
You know, I meant to bring them, and I don't know if I packed any up.
Okay.
It's possible Malcolm put a couple in.
Mm-hmm.
Yeah, we had a number of conversations about that, and I think I may have dropped the ball.
That is intriguing.
Okay, here we go. Here's one of your big sulfur samples.
Yes, that's good. We'll have a look at that. That can go in next.
But Malcolm's fear was that does putting it in the SEM disrupt or affect their ability to be used for isotope analysis?
And my answer to Malcolm was mainstream science says it won't.
Why? Okay. I don't need you to explain.
But we've got plenty of.
I'll let you see how much I have.
Well, what I'm saying is it shouldn't make more sulfur 34. So if we still see sulfur 34
Right.
after something that's like,
Right. Yeah.
they've still got to explain where the sulfur 34 came, and they go, well, you just put it in an SEM.
I mean, if you get a magical SEM that's making sulfur 34,
Yeah.
then that's another amazing discovery.
Yeah. All right, I think what we need to do is go and look at one of those blue spots. This is an interesting finding in its own right.
Yeah.
I don't know what it means that we have potassium and fluorine co-located.
And aluminum.
And aluminium, yeah. I mean, there's a stone's throw from aluminium. Actually, it's not. So, like, I don't know. It's odd. That's that, and the concentration is.
I mean, two carbons make magnesium plus one aluminum. Maybe, but you don't see any magnesium in there. What's interesting is they're all odd numbers.
Yeah. Not really, but yeah. Anyway, okay, all right. So
Not really. They're not all odd numbers,
Well, no,
or it's not
oxygen
interesting.
oxygen isn't.
Well, no, I meant the
Yeah.
potassium, fluorine, and aluminum.
yeah. What I found is if you start with a lot of one odd number, then if you add helium, alpha conjugate nuclei, you end up by going nitrogen to fluorine to sodium to aluminium. So it could be that our system has produced a lot of nitrogen, it's concentrated in here, and then the alpha particles are being added onto the nitrogen, right? I've seen this where we literally had PTFE, and we had all of the odd number alpha conjugate nuclei from fluorine that added on. And then there was titanium. This is when we put HHO on titanium, and then we put that onto a piece of PTFE. And so we got titanium plus alpha conjugate nuclei. So we went titanium, chromium, iron, nickel, so on. And then there was fluorine in there. So we went fluorine, sodium, aluminium, phosphorus, chlorine.
Huh.
So like we had two major elements in there, and each time they were adding alpha conjugates to them.
Interesting.
Yeah. So I think that's probably what's going on when you see that. Okay. And that was with HHO as well. Okay, so come out of that.
Is there any chlorine in there?
There is some, but yeah. Have they got any of this one? Not there. Not there.
No.
Not there. Where's the big map? The big map's up here. Yeah, there's some chlorine here.
Not much.
No.
Cool.
Where is it? Yeah, it's kind of a... Oh, no, it's actually concentrated on one part of the central structure. So, yeah.
What else is in that area?
It's got all the usuals.
When you look at it with the chlorine, you do kind of see a broader yin-yang to this thing.
Yeah.
If you take the calcium out, you can really kind of see it.
That's a story. Okay.
Yep.
Right, so we need to go to our overall map here and find out our blue spots. Give me a blue spot. The blue spots are down here, aren't they?
Blue spots, yeah, there's a couple of good...
We've got this similar structure here, actually.
Here, look on the...
Hold on, we have this similar structure here, don't we?
Where's this?
It's the other one that looks similar. I'm just.
The other sulfur
see
spot?
if we, yeah, I'm going to see
sure.
if we have a.
Oh, look at
Yeah.
that. What do you think? Think calcium and
I don't know,
sulfur?
but this definitely looks like something here.
Huh. Yeah, it sure does.
Where's that? That is part of this story here.
Looks like a couple broken spheres. Kind of looks like a sad snowman a little bit.
This is actually quite a large structure.
Is there disruption zone right here?
You know what? I'm gonna map this on a longer term map right now. After I've done a quick. Hold on, that looks like a little pipe there.
Yeah. Huh.
I like the look of that.
A little seashell.
I like the look of that.
What is that?
That is nice. I like the look of that a lot.
Okay, so you can see here. Yeah, so it's actually under the first samples where you get the
highest.
highest.
Now there's some very defined ones here, just under where we're looking now.
Yep.
So we'll go and have a look at those.
Sure.
Yeah. And you've got some carbonaceous ones here.
Well, these are equally defined, but I'm just not focusing on that.
Yeah, but I like the separation here. I
Yep.
always like it where you've got less confusion.
Sure.
But this is nice in its own right here, in this structure here. So I think we're going to do a map of this area.
Here's a better picture.
It's a great camera, that, isn't it?
Yeah, it's great. Really good.
Zoom into this one, look, because we're in this top right-hand corner here. Somewhere over here. Look at the center of it.
Yeah.
Yeah, we'll do a large... Look. That looks like that is the core. And maybe here, and this is the input. I don't know. Anyway, we'll get a better idea.
Where's this cone? This is up
somewhere
there, right?
Here, yeah.
Upper right. Oh, no, it's
No,
lower
it's
right.
actually down. It's there.
Huh.
It's these two structures.
And it's pointed towards it. Or away from
I
it.
need to rotate this so it's in the same orientation you've got that. It's here or here. It's one of these bits here. Anyway, we're gonna see what that is. I'm gonna save that as our fool's gold.
Be nice to upload some of these to have them on your screen so you could reference them
Yeah.
in the video. Maybe you can put that in post.
Yeah. Oh, I really like that camera. It's so easy to use as well.
Yeah.
It just delivers. Like,
Oh, that's a good one in this spot.
that is a good one. Yes, I like that a lot.
Hold on, let me see if I got a better one.
In the next image.
Oh, I think this is the best one.
Yeah, that's nice. That's very nice. So I think what we'll do is.
So I think it's flipped. You want me to-
Yeah, well, rotate yours around
Yeah.
and I can get this aligned. I'm just going to do a little map on this.
Because I think you're a little.
I'm going to do a little map on this right now.
Oh no!
I don't want to do that. I didn't want to do that. I'm going to do new.
Because in yours, I think it was it was giving birth out to the right side as well on yours, right?
Yeah.
The little blob guy here.
What have I got this on? I've got it on point now, haven't I? I'm just going to do a couple of points. Let's see what that is. Well, there's a lot of chlorine there. And this little spot has a lot of iron.
A little aluminum.
It's just this little guy here, but yeah.
A little nickel in there as well.
Mm-hmm. Yeah. When I see something like that, you could argue that it's contamination because it's just left lying on the surface.
Yeah.
When you have something like this that's growing
Right.
onto the surface,
I mean, that could still theoretically be. I don't know.
it could be a drop of stuff that goes on.
Like a metal shaving or something that's kind of turned into a little horn there. I don't know. It looks seamless though.
No, it's growing out of it.
Yeah.
And I've seen these things in ultra experiments, like growing out of the center of the vortex. Like it's a tube, kind of like a semi-tube type thing coming out.
I wonder if do you think you could,
Anyway, I'm going to orient it to the same as your image.
or I could switch.
No. We'll do the same as yours.
I think it looks like, well, yours looks like your baby's pointed up and to the right, kind of in a diagonal.
Oh, actually, it's I'm as close in as I can get here. By the way, I'm not far off actually. So
I think, yeah, close enough.
So I'm going to go to here.
Is that the baby there? Is that this thing?
That,
it looks like
that
it.
is our. Oh, I'm down the bottom side of it. It's actually that we need to do a map of this area.
That's not this right here.
That is where I am in that
Yeah,
bit. Yeah.
Cool.
So I'm actually in. I think
You're inside
this
it,
area.
yeah.
I like this little feature down here, which is out of focus on yours.
I might have one where that's in.
Don't worry. Don't worry. I can see a hexagonal type shape there.
No, that was not better.
You see how annoying that is to have that over the top It should be down there. You should just say, I want it in one of 4
It should
pages.
just be this big. It should just be a tiny little.
Or a little bar here.
Yeah.
Yeah. Quite tedious.
Huh.
Oh, I haven't got that on mapping, have I? Oh dear. No, it says it's okay, but it's not okay. No, it's okay. No, I'm gonna kill that. Put it on mapping. I'll just do a point sample.
In these pictures, you can really kind of see the broader structures.
Again, it has chlorine in it. A lot of chlorine going on in this.
Right, all these little like larger circles everywhere. And this is kind of like layered over itself or going this way. Iron, chromium, calcium. Usual stuff.
Okay. All right, I'm going to do a map on this. So here we go. We take this mapping tool here and we can say we want to take a map of this area here, and we can go like so, and we go like so. And then we choose the number of segments we want. So this is 4,000 times magnification. So this is going to take 1 hour and 32 minutes.
Oof.
So you've got to be pretty judicious about what area you're using. So if we go down like here, and then you can change your magnification or whatever. At the moment, I've got autofocus on. If this is fairly flat, if I've managed to get this fairly flat, then we can turn that off, and it's a much less time, right? And then you've got to say, well...
But you're kind of gambling, right? There's nowhere to really check
well, yes and no. You can't fix it afterwards, but it takes such a smaller fraction of time that you can afford to do it. Now, the question is, what is 4,000 magnification? Well, let's look here. At the moment, we're on 540.
So 4,000.
So 4,000's like here. So we can already see we're out of focus here.
Right.
So what do we actually need to resolve this? If we look at some of the features we were looking at over here. I mean, yeah, you see, it's not in focus, is it? So, like, yeah, you see, that's what we'll get if you're in focus. So possibly we need, because it's quite a large area, we might need to have autofocus on. Is it significantly out of focus here? I don't know whether it is. If we're going to go at 4,000, we're going to be there. Let's have a look at that point. It's starting to get out of focus here. Yeah, I think we want to be having autofocus. 4,000 Okay, that's an hour. I think we'll start that off. Do we need that? I'm going to actually pull that in a little bit more. Now, do we want to do one of these other spots here at the same time? Do you want to do one of these other spots? So we've already got one mapped.
Yeah, one of these blue guys.
Yeah, I think we're going to do that.
Yeah. I call them the Matis. They look like the Greek evil eyes.
Right.
I think any of them are probably good, but
Yeah.
maybe we want to get a particularly juicy one from the photo here.
Well, we can have a look to see if that one that I'm looking at there is any good. Can't really see it. This. I think we'll suck it and see. Okay. And the good thing is that actually as this builds it, you can see it and zoom around it whilst it's building it. So if it's no good, then you can... Yeah, so I've chosen this one, I think, or this one of these two. It's fine.
It's a nice saturated one right there. One of these.
Well, I think we go for one of the darker ones like this, like the straight dark ones.
Mm-hmm. I wanted to see one, just to make me feel better.
This is better. Yeah.
What, the sulfur one?
Yeah.
I mean, I have some that have like the extremely well-defined Matsumoto leoparding patterns.
Yeah. That's on the outside of the inside, right?
No, it's on both.
Oh, okay. Yeah, but the form of it's different on the inside and the outside.
Yeah, we got to get into some of the inside sphere today, because I don't think anyone's ever looked at the inside of the inside, right?
No.
Yeah, so we got to check that out.
Yeah, there's some fingerprint specials.
Yeah, not mine, not my fingerprints. I was very careful, but the very well.
I blame Johanna. If anyone, look at this lovely structure here.
Yeah.
Pentagon here.
Yeah. See these? These are like.
Yeah, they're good. Yeah.
Look at all that gold. It's rivers of gold.
Now I understand.
We're rich, Bob. We're rich.
No.
Yeah, this is the one.
No.
This is
You
the
see,
one.
the beauty of this then is once you've got these maps, you can click on this and it'll take you to that thing.
Yeah.
Right?
You can't normally do that.
Well, otherwise you're moving around very slowly.
Yeah, yeah.
Whereas with this, you can,
Right,
you can click on it.
If the whole thing's already resolved, right?
Yeah, and you can use this to find things, and so you're not sitting there trying to find things bit by bit.
Yeah.
So what we'll do is we'll get...
Here, check this one out, though. This is the one I was...
Yeah.
This is the one. Yeah, no problem. Look at that. Just had the Fury push it.
Patience.
Don't bump it.
Oh, look at this carbon filament here.
Nice.
This is a real sign. Look at that. These are the kind of things you can't do by just digging around, right? You have to kind of be patient, walk away from it and let it do them out. And then you can give these people, yeah, you know, got some action going on.
Yeah. And this is on that blue dot.
No, this is around the first.
This is a map of the sulfur spot.
Yeah, whatever it is.
So this is the irony.
This is the surrounding area.
Yeah.
Yeah, look, there's a.
Oh yeah.
There's a candidate.
I can see the crenellations from
Yeah,
from here.
You just might be dreaming it.
I dream of crenellations.
But look, like here's your typical smaller structure. You've got the sphere in the centre of the carbonaceous deposit on the outside. And these are like normally like silicon rich or whatever.
I want to check this one out.
Yeah, but
This one I showed you. This.
yeah, it's lovely.
Unfortunately, I cut it a little tight here. I wish I'd given it an extra a little bit, but you still get this kind of. You can see it's got a little THOR structure here. A little.
Yeah, it will be happening at much larger levels. Look, I think I found a good.
Because this whole structure is.
I think I found a good.
Oh yeah, there we are. I just want to see one.
You're gonna see one. Don't worry.
Oh, there we go.
Yeah. I mean, some of these might be it depends on the level of compression. Some will be silicon, some will be.
Mm-hmm.
Oh, I think that's a good candidate right there. I think that is.
Yeah. Oh yeah. Sharp.
Here, this one here as well. Look. But these are still relatively small ones. What I like about ultrasound is that you get very large ones. I mean, in our plasma reactor, we get very large ones, but they get messed up. They get remelted by interaction with plasma because they're going around. Whereas the water ones, they form coherently, and there's never any thermal melting on them.
Yeah.
So that's why you get these really beautiful ones in bin system and just the basic ultra experiment. Yeah, we're going to have plenty to look at there. Right, let's get the other one over here.
And you wanted that sulfur sample?
That one, yeah. Right.
There's two of them. I don't know. They're kind of basically both the same.
Let me have a look. Have you got macro photography of them as well?
Yes. I have macro photography of every single one of these pieces.
Okay, cool. Right. I think you need to get Malcolm to get you a new Mac.
I agree. This thing sucks. It's so old. I can't.
No, you need to get Malcolm to get you a new Mac. Then you can walk away with something that's tangible out of your experience.
Yeah.
Not just your expenses, paid, a little bit more debt.
I agree. So yeah, here's the two.
I think I like this one better. I like the waviness on here. This looks like water's distorted it after the fact.
I think they come from the same.
That's okay.
Bit.
I'm interested in this bit area.
Okay.
The transition between here and here.
Yeah, and you get these cool kind of reflective flakes.
Yeah, I know. Yeah, they're nice.
which is the other thing. You can see how much it.
Yeah, I know, I like them. Yeah. Okay, so
all that conversation.
we had some lovely conversation, but you didn't get to hear it because we didn't turn the mics on. But essentially, what we have found, which is really special, is these tubes, and we found them essentially because it did a map area. It did a huge map area, but we were trying to look at this structure, which is a large yin-yang type structure with multiple sub-yin-yang structures. But it was misregistered compared to the color graphic overlay. So we ended up by seeing these tube structures here. And when you look at them, it's just mind-blowing. Awesome. These hollow carbon tubes are, it would seem, definitely carbon right there, but they have nitrogen co-incident with the carbon. And so I'm arguing that these structures are deposited by the exotic vacuum objects, by the so-called plasmoids, and that implies potentially that it is synthesizing nitrogen, or at least capturing nitrogen inside. But this gives me hope for the fact that the nitrogen 15 over nitrogen 14 test might reveal some interesting data. There we go. That is the contrast between the carbon and the background iron. And if we turn that off and turn on the nitrogen, it's a similar story. It is co-located with this structure. And we also looked at a different area. So there's this area here, clearly carbon co-located with the nitrogen here. That's the nitrogen, and that is the carbon. Okay, so we're going to go and have a look at another one of these structures, but sadly, we weren't talking.
The boom. We'll have to superimpose the audio of the boom over that moment. And we missed all the fun of trying to pop those bubbles.
Yeah, well, no, that's true. You missed the reaction when we're blowing these bubbles up. Okay, so we're going to go and have a look at one of the other areas that's similar to this by going to our map area, and it's up here. And same kind of story going on up here, I think. Look at this thing here. Oh, is that not a thing of great beauty?
Did that blow up a little bit?
I don't know, but I'm taking a photo before I destroy it.
Is it moving?
Yeah. You're seeing things now. It almost looks like one of those party balloons where you've overwound it into too many party animals.
Right.
And it's got those blisters still left.
Exactly.
You know what I mean? This is quite special here. Like, so what have we got down this end of this? It comes all the way down to here and kind of...
It just puked. Puked out the carbon at the end.
Yeah, maybe. And it's got something up this end. How's it?
Oh, look, one of those horns. That's very interesting.
Yeah. And in this area, there was a whole bunch of little spermatozoa type ones, wasn't there? Down here.
I thought that was in the... Oh, yeah,
No, there they are.
Yeah.
There they are. So I think we will take a shot of this. And it'd be interesting to see what the difference is between the end of this. Mm-hmm. Right, what are the elements in the end here compared to this channel? This might be the carbon.
I wonder if that's really nitrogen heavy in the head.
Or heavier than that, potentially.
Yeah.
Like, have we got fluorine in here? Or have we got oxygen in here?
Yeah, because that's probably what's doing the work.
Yeah. And this is the tail behind. This is beautiful. This is totally beautiful. And it's smoothly blending here. It's going under this piece here, which should imply that, that occurred after this. This is really nice. It's totally lovely. I'm gonna
Don't pop them.
I'm not. I'm gonna try not to pop them. Oh, this is so cool. They literally look like little creatures, don't they?
Well, they might literally be little creatures.
Yeah, there's that. Right, I'm gonna do both. Oh no, I've moved it now. That's foolish. No, I'm gonna have to do that again. Yeah. Right, I'll do that because I want to get this SED and BSD.
I'm calling heavy nitrogen around the head. Around
Nitrogen.
Around the skin of the head.
I think we can do some spot detections on here. These are rather lovely, aren't they? Right, so we will do total SED to get some more look at the geometry here. They've got a very interesting head there, haven't they?
Yeah, and
it's like a little
side
nipple.
profile then.
Yeah. I mean,
Unless it's a little mouth.
Maybe. Whoa. Okay, so it's deep coloured on the end there. It's almost like it's refracting the material below. Look.
Yeah. Yeah.
Is it like a diamond fibre, a glassy diamond fibre? I shouldn't mention that.
No
should I?
D word.
No. Well, okay, we don't talk about the D word.
Structured nitrogen.
Structured nitrogen, of course. Yeah, we might only get this sample done today.
Yeah.
It's just the way it is.
We could. I do have that aluminum sample.
Yeah, well,
ready
we'll
to
try
go.
and put these on and then
Sure.
maybe do a couple of maps.
Do it.
tonight.
Yeah.
Okay, right. What are we going to do here? I'm going to take a shot of that. No, I'm not taking a shot of that. I'm going to put it in here. I'm going to do...
Do a map.
Yes. Do a map. I'm going to do it across the top of both of those heads there
Yeah,
to
there
get
you
an
go.
idea.
There you go.
It's like a control, not a control, but a, is it self-similar? What have we got? Yeah, the carbon's coming in.
So you get
Okay, look, that is definitely a helical twist. Look, that's going under there, that's going under there.
Yep.
So that is what's happening. It's a
Yeah.
hollow tube and it's helically twisting around as it's depositing it down. And so you're getting what looks like a bubble, but and it might have
It's just
gas
a side
in there.
profile.
Yeah, you're just seeing it. This is great because this is what you literally see on video in the Vega experiments of Hank Guerin and
You talking about the
David
coherent
Bouvier.
matter spirals?
Yeah.
Yeah.
So you're seeing something that died here. Look at that.
Wow.
Now, where is it?
Where is it?
Oh,
Oh no, it's back.
What? Yeah? No, that's calcium.
Nitrogen.
That's nickel.
Oh, nickel. Sorry.
Where's our nitrogen? There we go.
Yep, there it is.
Same story, my friend. Same story. This is good news for the nitrogen test. Really good news. Yeah, the nitrogen there.
Yeah.
Whew. Look at that. Beautiful little things. Are we still going on this? Yeah, it's still going. So it's building up a bit of extra fidelity here. They are quite special. And I'll have a last shot on the other one at the top there, above this. Do you see the value of taking the map?
Absolutely. Well, because it's really like you can't ever see the full story in the process until you do it.
That's how thin this shell is.
Yep.
It's really
Yeah, and so
thin.
what's the diameter of each one of these wide areas?
We
there?
can look at the wide. We can look at that.
I mean,
In fact, I'll tell you what. We do a 3D structure on this.
Now you're talking. Yeah, because then you'll actually see how much that's coming up.
Yeah. I'm gonna see if there.
You know, Bob, you're pretty bright. I gotta give it to you. I don't care what they say.
I'll pay you later. Someone's got to. Yeah, that's nice. That is nice. What did I do there? I don't know whether I wanted to do that. Oh, it's showing it differently there. Oh, that's nice. I like
And
this
so you
mode.
think it's coming up this way from the bottom?
That is
right
twisting
up.
that way.
And so it's twisting.
It's twisting to the
clockwise.
right. Yeah.
Right hand rule.
Yeah.
There it goes.
That is twisting. That's twisting. And this might be joining and following this one, but it died. That's interesting. Look, the chrome. That's interesting.
I mean, is it possible it's just we're viewing through the structure?
Yes,
to
it
see
could
the
be.
chrome?
It could be lensing. But definitely the nitrogen is in there in this material.
Yeah. That's awesome.
That is really cool. That's calcium flakes. All around here. Silicon. What else we got? There's a lump of aluminium down there. Yeah.
Very cool.
That's pretty special. Right, so are we done that? Because if we have, we're going to go and do a 3D map of this one. This one deserves to have some 3D action going on. Yes, we've done that. So I'm going to go back here and probably make that my center point. And then we'll go here. I think we can go in closer than that. Okay. We've got the whole structure there now.
Kind of looks like a pomegranate with the mouth kind of.
The interesting thing
forward
is,
a bit.
this clearly looks like it's spheroid,
Yeah.
but the tube coming out the back is tubular. You know what I mean? And I think the tube is that thickness, but as it's laid down, it's kind of like flattened out. You know, it's literally a tube, but it's kind of like spread out.
I wonder if the Evo maybe is only as big as the mouth here, but as it goes through, it's just kind of blowing the material out to the non-radiating boundary, which is what the total width of that ends up being.
Yeah, maybe. Let's give this a shot in the old 3D. Let's go. I mean, it makes you wonder whether there are different species of these creatures.
Malcolm says there's 100.
100.
Exactly.
That's very convenient.
At least.
You know what annoys me about that? It's not an imperial number.
That's true. 108.
Right, so, stop it. Can't remember what I'm looking at now. What am I looking at? Which one's what? Let's go back. That and that.
Yeah.
Not that.
Oh, where'd he go?
I don't see it. Is it?
Hold on.
Which one's what?
Did the
I'm trying to see where I'm rotating here.
frame of reference move?
Is it there? Where are my two heads? No, that and that and that. That and that.
I think
That's one head, that's one head.
that's
And
that.
what's that bit?
It's just the second lump.
It's the second lump, isn't it?
What's that?
Is it?
No, because these look evenly spaced.
You know what? I'm not living that one.
Hold on,
bro.
is this upside down?
I don't know. What I'm going to do is I'm just going to measure across there, and then I'm going to go and look elsewhere. I'm going to take a closer in shot. So that is 5 micron. That is one of our quantization type
Yep.
sizes. Very, very, very tight. Kind of, wow, it's got a big fall off there. Look at that. Right, so I want a little bit more fidelity on this. What are my settings here? Can I have a second? Yeah. Oh, right, I can see here. Why can't I see that? I can't see that. That looks like I'm looking somewhere else, doesn't it?
Yeah, this looks off.
That's not right.
That's what I'm saying. Did it move?
Yeah, it looks like it's moved. But, okay, I'm going to go here. I mean, the things are definitely there, aren't they? So I'm just going to put this head and this part in the frame. Right? So hopefully it's going to get it this time.
Well, you want to try to get this second twist in, though, because that was one that really showed this part, right? Because
Yeah.
this is really showing that rotation if we can get it.
Oh, I can see it now. Oh, right. Okay, so that is the spiral there. So it's really only slightly changing it. And that is the cross-section. Look, you see here,
Yeah.
but there.
So
I
how
don't know
far
why
up?
it's so dim, but anyway.
How far up is that coming?
Well, we can find out.
Not that far.
Right, so this is very flat on the, what this shows is it's very flat on the surface, and the spiral is coming around there, and it's going around on the backside there. So we'll put that there. So firstly, our other head is here.
Yep.
So we'll measure, this one's more on its own, so we can check the width on that easier. So we will do here across there, and we'll see where the big change is. Right, so it's kind of like across there, isn't it?
So it's really only maybe, what, 4 microns
I think it's
across. Yeah.
Yeah. No, it's not quite got there. Okay. It's of the order of about 5, but it's a little bit inside. Okay, and the other one is. We can do it on this, can't we? Okay. Actually, the head is there to there. It's 3.5, isn't it? Right, now we will get rid of those two and we will go across here and right. So as we go along here,
So how high is that?
right.
Not 3.
So that's going at an angle. That's showing it's going at an angle,
Yep.
right? And you're coming
But
down
does
here,
that angle rotate?
and does it go to the other angle?
No.
No, it's gone back to that angle. So is it going like that? Is it oscillating? It could be going like that. It's gone that way, and it's flipped that way, and then it's flipped that way. But that's what it shows you. Look,
Yeah, I
that's
know,
going at
I
an
know,
angle
I
like
know.
that.
That makes
then
less-
it goes, and then it goes up, down,
Yeah.
and then it goes back up the angle. So it's going. It's not rotating.
That's not rotating.
Is it going like that? You've got two structures doing that, or it's literally flipping. It's an oscillating. I mean, Ken Shoulders did say it was an oscillating monopole.
Yeah, that's true.
He did say that.
It'd be good to go a little further back.
We'll have a look at the other one, which is clearer. I'm going to save that anyway. It's not so
and it's
clear
not
on
very
this one.
high. You know, if it were rotating, you'd expect that would be elevated 3.5 to 4 microns, which it's really not.
Let's have a look at the other one. I'm going to save that for, I'm going to call this sperm just because I can't think of anything better to say right now.
That's
It's
we'll
what
know
I
what
look
you meant.
like. Come on.
There'll be no
I'm
confusion.
being fair here. That's what it looks like. We'll find a nice isolated section of the other one above.
Oh, the of the longer tube. Yeah, good idea.
I mean, it could be a substructure in it is hitting there and it's knocking it over that way and it's just hitting and hitting and hitting. It's bouncing from one side to the other rather than fully rotating. It would appear to look the same. Right. We'll come out of that and we'll go up here where it's very clearly doing something. Yeah, we'll go there.
Yeah, that does not look like pure rotation to me.
That doesn't look like rotation at all.
Especially because you got this kind of funky little.
Yeah.
I mean, it does look like it's rotating, but it also looks like there's it's got this sort of like bulbous periodicity seaweed thing happening.
But it's not. It looks like it might be going like that, but it also looks like it's just spreading out that way.
Yeah, maybe.
And we're going to find out because it's going to have a height. We can go a height from there to there.
Yeah, good idea.
And what am I going to do here? I'm going to do this. Oh, damn it. I've just moved it again. That's the only thing I dislike about this system. You can easily just knock it off. With the manual thing, you can't. It's physically separate. So I'm going to take that at a decent res. Okay, no chance for mapping overnight. It'll be using the source all night.
Using the what?
It'll use the source all night. All the time we're not doing anything, it'll be using the source.
That's too bad.
Yeah, whatever. It's just the realities. Okay, so I want to go and do a map on this. Okay. We can definitely see where our trail is there. Check out that. That is definitely showing our trail.
Oh yeah, it does go up quite a bit actually.
Yeah, right at the end there. So.
Well, I mean, even in those pinch points, it's definitely.
Yeah. So we're going to go from the center of that across the center of that to there.
So maybe it is twisting. Yeah, look at that. I don't like how it has nanometers on one side and microns on the other.
Well,
what's the conversion?
If they put that to, well, it's 1,000, isn't it?
Good point. Yeah, I guess you're getting much less variability that way.
Yeah, we can actually see. So that's going, it's varying in height by 200 nanometers. So that, you could argue, is the thickness of this. And that's what I said. It was like, the skin of these things are like about 100, 200 nanometers. So, and then the periodicity here is about the 6 microns or 5 microns. Like, it's going down, and it's going up. And that's going there. Okay, so 5 point, well, hold on. Okay. It's about 5.5 micron between those two. Is it the same over here?
A little more.
A little less, actually. Well, hold on, the center's there. So that, yeah, anyway.
They're pretty similar.
There. Something like that. There. Okay, and then we'll do a width across there. What is that? That's 100 microns. So is that double the thickness and it's just collapsed down like that? It's twisted round. Now the question is, if we move over here, is that going to be an angle and that's going to be an angle, or was that just the substrate? Is it just laying down on the substrate? So, hold on a minute. Oh, it's actually not changing. What?
Yeah, so it just looks like it's
It's a layer
a
that's not
lumpy-
much thicker. It's just changing in one aspect there. Like, okay, so that the profile's flatter there,
yeah.
but it's more
it
pointed.
goes up a little bit.
Yeah, but it's more steep.
Yeah.
It's a higher rise, so you're going to get that over here as well. Look.
Yeah, that goes up much more.
So that is going up. What is that? .400 micron there. Yeah, over here, it's going up 200 micron. So it might be that the thickness of this shell is 200 microns, and here you're only seeing, sorry, 100 microns?
100.
100 micron is the shit. 100 nanometers.
Yeah.
And here you've got, is that right? Yeah, so you've got two layers there. Now why is that thicker over there? Because that is 200, so 100 micron. And then here, that's still 200 micron. What have we got here? Right, it's gone from 2 to 288. Not helpful. Anyway, the point is it goes up and down, and it goes up and down more.
Yeah. At the pinch points.
And so what is the variability between there and there? That's the difference. That's the difference there. On the top of that to there.
About 150.
What's that? 213 to 394. It's getting on for 200. So that's between two. I'm trying to think what it is. It's still 2, but it's flat that way rather than piled up onto each other. I'm going to take another section of this. I'm going to save that. I'm going to take another section. Unless I can get an answer over here. I don't want that one. Can I get an answer over here? No. It's definitely thicker here. Or there's a bigger height relief map. Okay. I'll save that as well. Take one more height relief map of this, and then we will chuck in this sample, and we'll get you an iron-rich crenellated soup.
That's all I need.
Before the day is out.
It's all right. We got the carbon and nitrogen in the tubes.
Yeah, that's
so
beautiful. That's beautiful.
that's
and
that's
those
everything.
hexagonal structures with the sulfur and the calcium.
Yeah.
It's a big wins.
Yep. Yeah, just one sphere. For the hell.
You've seen some iron spheres, but you just haven't seen.
I just you know.
You want to see a beautiful iron-rich
I just want
crenellated
to see
sphere.
a nice, chunky, crenellated sphere. That's all.
I know.
I'm actually really curious about this. Is that okay?
Yeah, we can put that in. Yeah, that's cool.
I mean, tomorrow at some point or whatever.
Well, we can put it on the same thing.
Oh, is the sulfur one?
Yeah.
Oh, cool. Just take a quick peek.
Exactly.
Because have you ever seen aluminum as the witness plate for EVOs before?
Yeah.
Okay. Do they do anything?
Oh, look at this, how it's laid over this material and it's almost underneath it here. That's really lovely.
I wonder if it's like, as the EVO goes, there's a certain amount of material it'll store in itself before it has to poop.
I think there's a bit of that going on. That's
Right?
what I've seen a
It's
lot of times.
Eating, pooping,
Yeah,
and that's why you get these lumps deposited.
Yeah, maybe. It's just, it reaches a certain level and then
has to dump it out.
You know, you got to go when you got to go.
It's true. You can't eat.
Better out than in. Right, you might want to pack up things you
Tidy
need to
up,
pack up. Yeah. Well, we've really got separation here, so I'm going to go across there. So that is only 100 micron wide. Yeah, no, sorry, that's 2 micron wide. Okay, that's the right kind of width for these things. That's 2 micron, yeah. And the height is when it's just got, it's almost exactly 100 nanometers. Minus 395 to minus 296. Now, if we go over the corner, the cross section there, we're going from minus 475 to minus 237. Yeah, so I think the wall thickness is about, what would that be? It's about 50 nanometers of these hollow tubes. That's 100 nanometers, and that's for 2 sides. And that central bit there is piling up. Minus 475. 237. That's 250. Yeah. I think the wall thickness is about 50 nanometers. And when you've got it like that, it's kind of piled up, so it's a bit thicker.
Yeah, because you think it's kind of flattened down on itself.
This is flattened out, so you're getting double the wall.
Double, right.
You're getting double the wall thickness.
Yeah.
But this is like a whole bunch put into one place, so it's going to be variable. Yeah, that's cool. This is really cool.
And
You
where's
got-
your friend?
He's just gone to the.
He's gone. Okay.
Yeah.
So I go to the shop. I will be back in 15 minutes.
Okay.
And after we just turn it off. And,
Cool.
There are meetings, so I need to be there.
Understand.
And tomorrow
What time?
I am available from like 11, but my colleague Hinek will be here from 9:30.
Okay. All right. We'll come then.
He will be there and
Okay.
he will open for you. And I will come back like at 11.
Perfect. Thank you.
You have time to take a peek.
I'm going to have to take a peek. I'm just saving this off. And when that's done, I can take it out. You need to put it back in its bag. That's some major results, and it's just amazing that because of an error in the registration, we found these carbon tubes.
I know. I mean, they're probably everywhere.
Yeah, but you don't
But
know.
it wasn't elsewhere in that sample, right?
Well, there were several locations. It wasn't like a one-off. But they only came about because, you know, we were accidentally looking at the periphery.
Well, it's like you said with the other SCM, right? It's you find the best things when you're not looking for them.
Yeah. Right, I'm going to eject this sample. Yes.
Well, it may not have been gold, but it was special.
Yeah. It was special. I literally cannot believe it. I didn't even want to show the SEMs of Binja and Huang's carbon tubes last week, but I'm kind of glad I did. You know what I mean?
Well, because now you're kind of prepped.
Now it's not like...
Why didn't you want to show them last week?
Because I wanted to discuss them this week.
Well, now you get to discuss them both.
I know. But I can show his images.
Yeah.
I can show the ones from Huang. And I can show the one from Malcolm Bendel.
Now,
It's just freaking great.
did bins were more of a
No, they're
concise
tubes.
spiral, right?
Well, one was a
Were
spiral,
they
one
as-
was just a straight tube.
But it wasn't lumpy like these.
It was twisted like that.
But it didn't have these like seaweed things going on, right?
Well, it's kind of like
Kelp pods.
it is kind of that. Yeah, I really stuck that in well.
We didn't even do the blue. Oh, you get the map. Did you map it? No, we didn't.
Another day.
Huh?
Another day.
Damn.
I think there's blue on here, isn't there? Oh, we'll look at it tomorrow.
This was the only one that I found in the whole series.
we'll look-
that
we'll
had the
look
blue
at it
on
tomorrow.
Yeah, we gotta figure out what that is. Oh, hold on. Let me get you the that little aluminum guy too. You think we have room for it?
Yeah, we're gonna try and make room.
Are we looking at a pretty hard 4 p.m.?
Yes. And he just came in to confirm that it's going to be a hard 4 p.m.
Don't blow the aluminum too hard. We'll blow those flakes right off.
You have to be 4 slices down from the highest point so you don't crash the head and cost 30,000, 40,000 pounds worth of damage. If you get everything packed away,
Yep.
so you're ready to go,